Hey everyone, welcome back to the channel. Today we were going to continue quantum computing topic, its real world application and what can we do with that. First, let's kick things off with what makes quantum computing so special. Unlike classical bits, which can be either 0 or 1, quantum bits or qubits can be in a superposition of both. Imagine being in two places at once, that is superposition, and it's get different. When qubits become entangled, they share a connection so strong that measuring one instantly affects the other, no matter how far apart they are. This means quantum computers can perform many calculations in parallel. It's not just about speed, it's about solving problems in a completely new way. Let's see where this strange new power is already being used. Now, let's talk about cryptography. Most of today's internet security, like RSA encryption, is based on how hard it is to factor large numbers. Enter quantum computing with Shor's algorithm. It can break this encryption shockingly very fast. That's a problem. But quantum also provides a solution, that is QKD, which is known as quantum key distribution. It uses quantum principles to exchange encryption keep securely. If someone tries to intercept them, we know immediately. It's like sending a message in a bottle that explodes if someone touches it. Here's a game changer drug discovery. Simulating how molecules interact is super hard for classical computers, but quantum computers, they thrive here. They can model complex quantum systems like the folding of proteins or how a drug binds to a receptor. Companies like Roche are already using quantum simulations to speed up R&D. We are talking about faster cures, more precise medicines, and possibly even predicting side effects before human trials begin. Finance meets quantum next. Imagine trying to simulate thousands of potential market outcomes. Your computer would crash just thinking about it. Quantum computing can run these Monte Carlo simulations exponentially very faster. Banks like Goldman Sachs and JP Morgan developing quantum models for optimizing portfolios, managing risk, and even predicting fraud. That means better decisions with less guesswork and maybe smarter investments for all of us. Now let's throw AI into the mix. Quantum machine learning combines the pattern finding magic of AI with the parallel power of quantum. Instead of slowly training models with mountains of data, quantum processors can explore solutions much faster. Quantum neural networks could one day identify cancer in images faster than radiologists or predict customer behavior with scary accuracy. The potential here is huge, and we are just getting started into it. Ever used a map app and wondered how it finds the fastest route? That's a type of optimization problem, and it's get really complicated with delivery trucks, warehouses, and time windows. Quantum computing shines at solving these complex problems. Companies like Volkswagen and DHL are already piloting quantum powered logistics. The result is faster routes, lower emissions, and packages that show up sooner. Quantum computing is also revolutionizing how we design materials. Think about batteries that charge in seconds, or superconductors that work at room temperature. By simulating atomic interactions, quantum computers can help scientists test our new compounds in a virtual lab before they ever touch in a beaker. IBM are already doing this to build better, greener materials. It's like having a chemistry lab inside a quantum chip. Sounds different, right? What if we could predict the weather more accurately, days or even weeks in advance? Quantum computers might help us to do that. They are excellent at modeling systems like the atmosphere. By processing more scenarios in parallel, they can improve forecast, warn about storms earlier, and even model climate changes decades into the future. Organizations like NASA and NOAA are exploring this right now. Now let's talk reality check. Quantum computing isn't quite ready for prime time. Qubits are fragile, they lose information easily. That's called decoherence. Also, scaling quantum computers is hard. We need thousands or millions of stable qubits to tackle real world problems, and we are not there yet. Plus, many quantum algorithms are still in the lab. So, for now, it's about hybrid models where quantum computers do the heavy lifting and classical computers handle the rest. So, where we are headed? Experts predict that by 2030 we could achieve quantum advantage where quantum outperforms classical in real world tasks. This revolution could transform energy, healthcare, cybersecurity, finance, and even climate resilience. From the US and Europe to China and Japan, the race is on. And as these systems mature, they could become a pillar of 21st century infrastructure, right up there with AI and the internet. So, are you ready for the quantum future? Thank you.